I'm going to present my analysis of series elastic actuator under the activity of modern control theory course. So what is a series elastic actuator? So in normal rigid actuators, the motor shaft is directly connected to a gear transmission, and which is directly connected to a load. So when there is an impact, there is a high chance that either the shaft or any of the components of the actuator may break. So we introduce a compliant compliant mechanism in between to increase the impact load to increase the uh, impact load that the system can handle, as well as it improves the force sensing capability of the actuator. Now, this is the mathematical model of the system with state space variables as the uh, theta L dot, theta M, and theta M dot, where theta L is the load side angle and theta M is the motor side angle. N, where J and B J refers to the respective inertia, and B refers to the respective damping ratio. Along with that, the N refers to the gear reduction ratio. Now we have taken an Archimedean. I have taken an Archimedean spiral spring, which whose stiffness is not a constant, rather it linearly depends on the deflection in the spring. That is, it is given by B, the spring stiffness is given by B into theta S, where theta S is theta L minus N inverse theta M. Now, since this is a non-linear system, so we have to linearize it. So I have found the equilibrium points as given below. Now, there is a relationship between theta L and theta M. So I have assumed theta L to be minus 25 degrees Celsius, and corresponding to that, I have got the equilibrium theta M. Now, the linearized model looks like this, and this is the state space linearized model. And the output that we are getting from this is the load side angle and the motor side angle. And the inputs to this system are the load side external torque and motor the torque introduced by motor. Now, for the analysis of the model for this open loop system, it has one positive eigenvalue. Even if it's very small, it is still positive, which makes this model unstable. The controllability matrix and the observability matrix both are full rank matrices. Therefore, the model is controllable as well as observable. Now, this is the controller design, that is state space feedback control with observer. So using the pole placements that we require, that I have assumed, that is -5, -5, -10, and -15, -20 at the controller side system pole placements, and for observer pole placements, I have taken -5, -10, -15, and -20. And using that, I have calculated the K matrix and the L matrix, that is controller gains and the observer gains. And after employing that, the simulation results looks like this. The left one is open loop response. That is, since it is an unstable system, so the response is continuously increasing, even for a step response for motor torque and load torque. Whereas for the state feedback controller response, within 1.5 seconds, the response damps down to the equilibrium point. That is, for load angle, it is -25 degrees, and it damps down to it. So we see that without a controller, the response is increasing, and with controller response, we get the desired results within 1.5 seconds of the time interval. Thank you.